All right. So, exciting lecture today. Exciting because this is actually, I don't want you to cry here, this is actually the last video that we're going to make for this class. So this is the last one you get to watch, but don't worry, it is last but certainly not least. We're going to be talking about finite state machines. The first step of every lecture is to figure out the acronym that we use. Pretty obvious three-letter acronym here, FSM, for finite state machine. What a finite state machine is all about is we usually talk about application, right? We talk about how to use a PIC, how to use a logic gate. Finite state machine is like an abstract way to think about problems. So it applies to logic gate stuff. You can do stuff with finite state machines, logic gates, PIC controllers, and the way we're going to use them is we're going to do some PLC projects in your next lab. You're going to do some PLC projects with finite state machines. The whole idea behind a finite state machine is if you have a program that behaves differently at certain times, like it's got a state where it responds to inputs in a certain way, and then a different state where it responds to inputs in a different way, those are good examples of finite state machines. What they look like is they look like graphical representations. So these finite state machines, I kind of picked off a very basic example just to kind of start things off. And so this finite state machine, it's got two states. So this is the finite state machine for, you know, like a light switch on a wall. So this light switch is or it's off. I think this particular light switch is off when it's up, and then it's on when it's down for whatever reason. So this light switch has two states. It is either on or it is off. States are always represented with like circles or rectangles. This one's using kind of rounded rectangles. And then transitions between states are represented with arrows. So this one, again, we started very basic, right? This one you can transition to the on state by taking this action. So the arrows are actions. You could also think of them as inputs. And then, you know, you can make it go off by lifting up. If you continue to lift up while it's still up, you don't go anywhere. You stay in the same state. And so this is a very simple finite state machine. There are some details left off of this just to try to make it a little simpler. We'll learn some more detailed things as we go. So let's kind of step our way into this a little more. And we're going to look at another simplified finite state machine, but with a little bit more detail. So what we're going to look at is a finite state machine for a cassette player. The first question is, what is a cassette player? Nobody uses cassette players these days. I like the example, so you're going to deal with it. So this cassette player, you could play a tape on either side. They have like a side A and a side B. And so this finite state machine is broken up into 8 independent states. 4 states that relate to side A, and then 4 states that relate to side B. So I don't even know who still has cassette players, but this is a good finite state machine for how they work. So the basics of the finite state machine, assuming you can read through this thing, is if you're playing and you push rewind, you drop to the rewind state. If you press fast forward, you drop to the fast forward state. If you press stop or get to the end of the tape, EOT is end of tape, you'll jump down to stop, and if you push play, you'll hop back up to play. So side A stuff seems pretty logical and reasonable. And then if you press the reverse direction button, it'll reverse and come down to playing side B. And then side B has a lot of the same games, right? You can rewind, fast forward, stop, come back with you hit play. The important distinction is here and where finite state machines really become valuable is the same action might have different consequences from different states. So let's just look at, so if you press the rewind button, it depends on what state you're in, what action it takes. So it's the same button, but that button has different consequences depending on what states you're coming from. And I'll say this is the primary time when you need a finite state machine, when the same button does different things. And this is very common in games, right? So like if you hit start when the game is sitting there waiting, the start button does something, but if you press start during the game, it has no effect. And so things like this might be useful situations for finite state machines. So you actually have already done a finite state machine in this class. You simply didn't draw out all the states and things like this. So the finite state machine that you already made is the button press program, if you can think back that far. So the button press program, we had this situation where we had an input button, and it would sit here in, I guess actually I should say, it would sit here in the unpressed state. On the PIC-DIM, unpressed was a high voltage. And then at some point, it would hop down into the pressed state. And the reason we did this is because we wanted to take some actions that only happened right on that change. So we were like switching the buttons. And so to implement this situation, we had the following code. We had a variable that was called recent button state. I kind of snuck in the word state there back when we did this. And the recent button state could be in one of two situations. It could be pressed or it could be unpressed. So overall what this code did is, you had a chunk of code here where it was pressed and a chunk of code here where it was unpressed. And the main thing you did in those sections is you set the variable to reflect the states. Now the one thing this program also did is if you had just come from the unpressed state, then you had stuff that you wanted to do once and only once. And that was what was happening on this edge. So I'll tell you what, see if you can take a minute and fill out what this finite state machine would look like. We'll do it together, but take a quick stab at it, and don't make it harder than it is. So if I was looking at this finite state machine, I would start off and I would say to myself, all right, there are two states. There is an unpressed state, and then there's also a pressed state. And the way you toggle between them is you simply press RA4. So, you could say RA4 goes high or whatever you want to say. And then you would hop back to the other state. You would hop back when RA4 was released. Usually you show RA4 being released with an inverted signal over it. So like whenever you released RA4. I'm not going to get into the details of when it's high and when it's low. We'll just kind of show the basic ideas here. So if when it's released, you go to the unpressed state, and then when it's pressed, you go to the pressed state. Just to show you a few more details about finite state machines is within every state, you always divide it into two sections. So when you're dividing it into two sections, the top section has information with the label, and also sometimes you need to associate a number with every state, so it would have a number. And then below the line is output information. So for instance, when you were in the unpressed state, you turned off all the lights. So let's say when you're unpressed, you wanted all the lights to be off. In the same way that states can have a line and then outputs below, you can also have a line on actions. The line on action is optional. So basically, you have an input or an action, and then you have outputs that happen during that transition. So in this state, you had the do stuff once. And so the stuff we did is we would do things like we would change the light and things like that. So the finite state machine for this guy would have two states, and then an action that would take you between them. And then within unpressed, there was stuff that happened during the unpressed time, and then during the transition, there was stuff that happened then as well. So I went ahead and stole a figure from Wikipedia just to kind of make this thing more clear. And you can see that the way they label it is states are shown as circles, transitions are shown with the arrows, the transition condition is the thing that makes it transition, and then the action, the entry action is what they call it, is what takes place during that state. You can also see that they've gone ahead and numbered the states, which is something that we're going to do that makes these things easier to actually build. So let's look at a couple more examples stolen from Wikipedia, and we'll talk about some names here. So when people talk about finite state machines, you will inevitably hear the words Mealy and more. Maybe you'll never work with them ever again your whole life. But if you do, these are the popular catchphrases. Maybe you can impress somebody, at a job offer with your knowledge of finite state machines. So all right. So a Moore machine is a finite state machine where all of the actions happen continuously during that state. So there's just an action that happens anytime you're in that state. If you're in this state, the motor is on. That's just how it is. And when we talk about the Mealy, you'll see what the difference is. So this particular example is like an elevator door opening and closing. So these elevator doors, they can slide back and they can begin to open. And then when they are all the way open, they would hit a sensor that says, "Hey, we're all the way opened." And so that's kind of the whole idea. And then if you were to push the close, they would begin to close. They would be closing. And then when they're all the way closed, they could send a signal that says, "Hey, we're all the way closed." So if this were a finite state machine, let's just start at the top. So you would have a state where they're completely opened. So this is the open state. And if you press the close command, they'll start closing. And once they sense that they are completely closed, they'll enter the completely closed state, which I've also drawn up here at the top. If you say open, they'll hop into the opening state. And if you can also jump from the opening process immediately to the closing process. So there are two states that actually have motors driving, and the two states that actually have motors driving are states 2 and 4. So the motor is actually driving, and so they have stuff below the line there, right? So this might say like motor clockwise, and this one might say motor counterclockwise, because that's what's happening in that state. All right, so that seems to make sense, right? The other type of machine, and the reason we're kind of doing this example for you, is what's called a Mealy machine. So a Mealy machine has only one difference. The one difference between a Mealy machine is that within a state, outputs are conditional upon inputs. So within the state, the only difference is what's legally allowed to go in this area. So things that are legally allowed to go in this area are basically, they can depend on if statements. So let's say you had the motor close command. So we're going to put something in here. If we have the motor close command, we would start up the motor going counterclockwise. I just use some short here for motor going counterclockwise. So the difference is, in a Mealy machine, you can have if statements within the state. So this says, if we get the door close command, start the motor going forward. So this is like the then statement. So it's like an if-then. This colon is actually very common for saying an if-then statement. And then, in this area, if you get the motor open command, you would start the process of turning the motor clockwise. I may have not been consistent about my clockwise and counterclockwise, but you get the idea, right? So the only difference is you stay inside the same state. You don't leave states, and you can have conditions within the state. The advantage of the Mealy machine is that you have fewer states, which is sometimes handy. The advantage of the Moore machine is sometimes it's easier to think about. And to be honest, they're so closely related that I use them rather interchangeably, right? But I just thought I'd let you know the vocab terms, just in case you ever talk to someone about finite state machines. So let's have you do an example again. So in the quiz recently, I had you do a little example that dealt with a finite state machine. In the quiz, what I had you do is I had you finish the finite state machine, and I'll just go ahead and finish this up here. Hopefully your solution in the quiz looks something like this. So the idea of this project was that you would toggle which marker was on. So if you were, give me a second to finish drawing it here. If you're on this top line, and you saw, so you were in marker 1 state, and you saw an I1, you would abandon the marker 1 state and set marker 2. So that's what you did at that point. And then these other lines were continuing to move you through the sequence. If you're in marker 2, you would set marker 3, and you'd clear off marker 2. And then last but not least, if you're in marker 3 and you saw an I1, you would reset marker 3 and you would move to marker 1. So this guy represents a finite state machine. See if you can draw what that finite state machine would look like here. So, all right, hopefully what you managed to come up with is a 3-state finite state machine, where in the first state you have marker 1, then marker 2, and marker 3. And the way you transition around this guy is you see I1 getting pressed. At present, this is the solution to the problem. So at present, we're not actually controlling any outputs. If we wanted to, let's say that while marker 1 was on, I wanted Q1 on. So this wasn't in the problem statement. I'm making it up now. So if we wanted when marker 1 was on, marker Q to be on, we could have written that line of code, with the contactor. And then let's also say if we were in the marker 2 state, I only want Q2 to come on when I'm in that state and I'm pressing I2. So by adding this conditional thing, I've made it a Mealy machine, right? But hopefully that difference isn't too extreme. So this is an example of a 3-marker program. And I think that hopefully that's kind of building on things that are going. And so part of every finite state machine kind of looks like this. And the way this works is you have inputs, and they go into your state transition table. And your state transition table sets what state it is. And the current state also is important in figuring out what state you're going to go to next. So you have a combination of inputs and the current state, and that's how you figure out who comes next. Then with the Moore model, the outputs depend on just the current state. And then in the Mealy model, the outputs depend on both the current state and the inputs. So, all right, the big final challenge. So the big final challenge is to construct a combination lock that will take in the numbers 430, and if you press the numbers 430 and then press enter, a green LED will come on. So a green LED will come on if you hit the buttons 430 enter. If you do something else, you will go into some other state that will correspond to failure. And if you press the red button while you're in the failure state, if you press the enter button while you're in the failure state, you'll see a red light come on. So if everything's good, you type it in and hit enter, green light. If you do something bad and try to hit enter, red light. If you ever type in something wrong, the only way you can clear it off is to hit the clear button. So this is going to take you a little bit, but I think it's a really good example. So take a little bit of time, read through this screen, this slide, and see if on the next page you can construct a finite state machine that will perform this task. So take a little bit to do that. All right, so in the space that's marked improved solution is just in case you didn't get it perfect, right? So in the improved solution, let's talk about what this thing should look like. So it's going to have one state that's kind of the ready state, right? So this is where you would come on a reset. So you would start at this location, right? Now, from here, we have our good states. So we have our, you've hit the 4, and everything is good. We have our state where you've hit the 3, and everything is good. And then, you hit the 0, and everything is good. And then if you press the enter button, at that point, you have success. So at that point, you would have success. Now, if at any point in time you don't do these things, you will drop into a failure state. So these are basically the states that you can be in. You can be ready to go. You could have already gotten the 4, the 3, the 0. You could have success, or you could be in like a failure area. There are a couple deviations, but I like this solution. So basically, in order to transition from ready to the for state, you have to see the number 4. And I think we could make that kind of happen all the way through. So this kind of represents the awesome path of goodness. And you get this success, and during the success state, we do have an output. Our output is a nice, pretty green LED. So I'll just say in here, green LED. So once you have done the combination, green LED, goodness. Now, if you push something else, you will lead to a state of badness. So let's say that you are in the ready state and you push any other number. So let's say you press 3 or 2 or 1 or 0, or let's say you press the enter button. All of those would divert you to the failure state. Likewise, every other state has things that would be bad for it. So if you're in the 4 state and you press a second 4, that would be bad. If you press the 0 or a 1 or a 2 or enter, those would be bad. And go ahead and make yours up to date as well. If you're in the 3 state and you press any of these guys, that leads you to failure. If you're in the 0 state and basically you press any number, that'll lead you to failure. And if you're in the success state and you press enter, you could argue how you wanted to do this, but I'll tell you what, just for giggles, let's say that if you press numbers after hitting enter, you could also go to the failure state. That's optional. However you wanted to do that is fine. Now, if you hit clear at any point, so I don't care where you hit clear, you should go back to the ready state. So everybody's got their clear path. So clear here, clear there. Finite state machines get notoriously messy, right? I'll tell you what, let's send him around the top. Let's just kind of merge these guys in with them. And then I'll tell you what, let's bring him all the way around and merge him in as well. So if you hit clear, those will all take you back to the ready state. As far as outputs go, we have a green LED during the success state. And then during the failure state, you only have the red LED when you press the enter button. So if you press enter, then you get the red LED that says, hey, you messed up. Because we don't want to tell people immediately that they messed up. We want them to try to press enter before they even know. So this finite state machine represents what I would consider a very acceptable finite state machine for the ME430 lock. So hopefully yours looked a lot like this initially, but if it didn't, it should hopefully look more like this. And there's always a chance I made a little goof somewhere, but I think it looks pretty good. I suppose I could also say that if you press enter and you're in success, you stay in success technicality. So all right, the next question is, we've built this thing, like we've drawn this finite state machine, and it's cool. I'm happy about this thing. Now what? I mean, we've got to do something with it now. So I'll say that you've already got some practice with implementing a finite state machine, because you kind of did the reverse earlier. So the way you implement a finite state machine is in PicoSoft, every arrow is a rung. So this program, you know, every arrow was a rung. So you had to look at what state you were coming from and the action, and then you had to transition to the next state. So here, you know, you had to turn off the old one and turn on the new one. So what we're going to do here is actually very similar. And what I've got in PicoSoft already made is this finite state machine that I've already put in. So let's go look at the simulation. So the simulation for this guy, if I hit play and I look at the markers, is he starts off in the ready state. And if I hit the button for 4, he drops into the 4 state. If I hit the button for 3, he drops into the 3 state. I don't have a 0 button, so I made button 8 my 0 button. Sound all right? So when I press 0, he goes into the 0 state. So he's walking himself. Suppose I should bring the picture back up. He's walking himself around the diagram. He started it ready, and he's just kind of working himself around. And then I made the enter button button 5, because I only use 4, 3, 2, 1, and 0. So if I press enter, I drop into the success state. If I look at my cues, my green light is on. So how did I do this? So the way I did this is I started off by numbering all the states. So I find it easiest to go ahead and number the states. I used a very clever numbering system. I made ready number 1, and then number 2, number 3, number 4, number 5, and then number 6. So they all got a number. And what I did is, for each number, I have on the marker corresponding to that number and no other markers. So let's just look at one of the lines that I did. So it's about to get messy, right? So this first line here, when I jump from the ready state to the 4 state. So what has to happen there? So marker 1 has to be on, and I have to have an I4. So my top line of code looks just like that. I'm in the ready state. I see an I4. The action I take is I set marker 2, because that was the next marker, and I clear off the old one. So you can see my top lines are all the same. These are following the green arrows around the circle, right? So 0 and then enter, it goes to that state. Then some states you can build quicker. If I press clear, it doesn't matter where I'm at. I'm going to set marker 1 and clear the rest off. So that one was nice because all these little orange or orange-brown, whatever you want to call them, I built all of these guys in one big swoop. So if I press clear, go to the ready state. Then I do my various failures. If I ever press I1 or I2, I'm going to set the failure state and then reset to my R, my reset everybody else. So that actually takes care of all these big dark brown clear lines. And then I've got all the other methods for failure, right? So if I'm in marker 1 and I press 3, 0, or enter, so if I'm in marker 1 and I press 3, 0, or enter, I go to failure. I've already done 1 and 2. So basically, I've just got to take my figure, and I've got to start making all the if statements, right? So I go through here and I make all the if statements. And then down at the bottom, I do my below-the-line information. So if I'm in state 5, I have a green light. So if I'm in state 5, I set Q1, which is my green light. And if I'm in marker 6 and I hit the enter button, So if I'm in marker 6 and I hit the enter button, that would show me the red lights. So let's just simulate that real quick. So if I hit clear, and then I hit the number 1, it's going to drop me into failure. And then if I try to hit enter now, it's going to pop up my red lights. The last part of this code, this is what I call the cheater code. So when you start up MPLab, or start up PicoSoft, it starts with all the markers off, right? I wanted to cheat in this program, and the first state I want marker 1 to be on. So my cheater code kind of looks like this. If all the markers are off, then I want to set state 1. Now, it would have been swell if I could have done this all in one line. So I could have said, if marker 1 is broken, marker 2 is broken, marker 3 is broken. I would have loved to have put marker 4 is broken, marker 5 is broken, marker 6 is broken. But PicoSoft is rather limited. You can only have 4 items per line. So I had to make these temp variables as kind of some cheater code. So if these guys are all off, set a temporary variable. If these guys are all off, set a temporary variable. And then if both temporary variables are on, then kick me into marker 1. So this cheater code does the reset. So when you hit play, the first thing that will happen, and it'll happen quick, is it'll go through this. If you watch that really fast, they went red, it set marker 1, and so that kicked you into marker 1. So that little cheater code is only necessary if you want your reset state to kick you into a state where a marker is set. All right, so finite state machines are sneaky because when you first see them, I was the same. I was like, well, this is neat and all, but I never need it. I'll say that it's the gift that keeps on giving. I wanted to do a project just the other day for some junior high students, and the way I tackle everything is I conceptually tackle it with a finite state machine first. So it's amazing. I've got my little system down. I tackle with a finite state machine first. After that, I write pseudocode, and pseudocode is basically I just go through with a bunch of comments, right? So I say like what I want to do in English, right? So I say set up, digital outs or things like that. So I always do a finite state machine. Then I write my pseudocode, and then my third step is I just start writing in my actual code. And that's the way I approach a lot of the programs I run. Finite state machines are sometimes overkill. They're really only useful if the same button does a different thing at different times. So like if the same button doesn't always have the same action, you probably want a finite state machine. So a lot of the labs you didn't need them. But for your project, it really might be helpful. If I was tackling 90% of you guys' projects, I would conceptually think about the finite state machine first. Once you get good at them, it just gets your thinking organized better, and it makes your code cleaner. In class, what we're going to do is I'm going to show you some example code where I've implemented the ME430 lock on a PIC. You can do the exact same strategies with a PIC. I started with the exact same finite state machine. It's just the way I implemented it was different. All right, so that is the end of this lecture, and that is, most unfortunately, the end of video lectures for this class. What a sad day. When you take the quiz, try not to burst into tears or anything, so try to be strong. All right, that's it.